Assalamu alaikum students. In today's lecture, you will learn some of the examples of VESPER theory and how to write them in exams paper. That will be explained along with the postulates of VBT, including the postulates and then formation of sigma and pi bonds and their differences will be discussed in today's lecture. Now students, we have learned about the VESPER theory in the previous lecture. In VESPER theory, we consider that in the central atom, it is surrounded by that of the number of electrons which are present in its outermost shell, and then it has some bondings with that of the other atoms which are represented by the dot forms in the form of the pair of electrons in between the bonded atoms, that is central atom and the other one atom. There may also be present some lone pair in the outermost shell of the electron. The geometry of the lone pair of electron and for the central atom, right? Now the geometry of the molecule depends upon both, that is the lone pairs and bond pairs. Their repulsion actually makes the geometry. The minimum should be the repulsion, so they are placed at such a distance that minimizes the repulsion between them, as all of them are the electrons. So the repulsion should be minimum among them. The three types of repulsions are there within the molecules which they can face, that is the lone pair to lone pair, which has a maximum influence on the molecule. There can be second one where lone pair to bond pair is also, and the least one is of the bond pair to bond pair repulsion. The geometry is determined on the base of all these three repulsions, right? Now here some of the steps are given for the prediction of the geometry. The first of all, there is the determination of the central atom, that within a molecule which one will be the central atom. As I told you earlier, that is represented in general as A, B type. A is the central atom while the B is the attached one atoms with the central atom, right? Or if I consider CH4, here you can see C is the central atom which is having the number of other atoms attached with it, right? So this one is termed as the central atom. Then you have to draw the electrons dot structure around this central atom. Find out the arrangement of electron pairs which are formed due to the presence of the bonded one atoms. Then find the arrangement of the bonding pairs, how they are placed over there, and then we can determine the geometry depending upon whether there is present only the bond pairs or may there also be present a lone pair or more than one lone pairs are being present within the molecule. That will determine that what will be the geometry of the molecule. Now here it is telling you that as you have learned about that there can be present 2 electron pairs, 3 electron pairs or 4 electron pairs, that can all be the bonded pairs, or maybe there are present some lone pairs. Here I'm going to discuss only those which have only bond pairs, right? Now this is the way that you have to present in the exam. You can be asked that what is the geometry, or discuss the geometry of BEH2 or BF3 on the base of the VESPER theory, that which type of the geometry you will exhibit, how many bond pairs will be there, how many lone pairs will be there, and what will be the angle, right? So this whole description you have to write in the paper regarding these molecules. Here is given the answer. Well given answer is this one. This one is the, when in BEH2, if you are going to write here, the BE is the central atom, so you should know the electronic configuration of this atom. Here it is given, it is 1s2 and 2s2, right? 4 electrons are present in its outermost shell. 2 of them are present in the outermost shell while 4 are in total, right? These two are the separately unpaired electrons, so it can hold 2 hydrogen atoms along with it. You can see here the 2 hydrogen atoms, they are placed at a maximum distance apart from each other due to the repulsion. The only repulsion present in this molecule is bond pair repulsion, as beryllium is using both of its electrons which are present in the outermost shell to make bonds with the 2 of the hydrogen atoms. So it is given BeH2 with the angle of 180, and the geometry given it is a linear one arrangement or a linear molecular geometry it will hold. Similar arrangement will be there if hydrogen is replaced by chlorine. For BeCl2, you have to give same type of the structure, right? You can write it as it is AB2 type, that central atom with the two other bonded atoms with no any lone pair present in it, right? Similarly, look at the second one example. Here it is given the BF3 molecule, BF3. BF3 fit to the arrangement that is AB3 type. Here all the three electrons which are present in its outermost shell. Look at the configuration of boron. It is 1s2, 2s2 and 2p1. In the outermost shell there are three electrons which are unpaired, and all the three are bonded with that of the fluorine atoms individually. Three fluorine atoms are present in it. The maximum repulsion which they can give, that is with the angle of 120 degrees, and the geometry will be a trigonal planar geometry. Now remember it, none of the lone pair is present in it, but all of them are the bond pairs. Now, if you are asked that explain that which type of the geometry CH4 or methane holds or the PCl5 holds, then you have to describe it in this way, that the CH4 comes under the heading of AB4 type, in which the central atom is the carbon atom holding four hydrogen atoms around it with the four bond pairs. The geometry or the what you say, the molecular one geometry which is given, the structure which is given by this molecule is tetrahedral. Why it is so? It is in accordance to the electronic configuration of the carbon, that it is a 1s2, 2s2 and 2p2. One of the transitions from 2s to empty p orbital makes unpaired electron 4. So these four unpaired electrons, they get bonded with the hydrogen atom by sharing one electron pair with each, right? So here the formation of four bond pairs takes place, which determines the geometry. There is present only one type of repulsion, that is bond pair to bond pair repulsion. No any lone pair to lone pair repulsion is present. So the tetrahedral geometry is present for methane, and bond angle between these bond pairs according to the repulsion will be 109.5. AB4 type presents that there are only bond pairs, none of the lone pair is present. It's telling you the category, right? That the central atom is with four electron pairs in it. Okay, now the similar structure is given by CCl4, right, or CHCl3, but that will be a little bit distorted one. Okay, now come to the next one. Here it is telling you about the general one term, that is AB5 type of the bondings. There are present 5 electron pairs around central atom, right? Here you can see the example is given of PCl5, as the name is indicating AB5. So the central atom is phosphorus, which is linked with 5 of the chlorine atoms, making 5 electron pairs surrounding the central atom. They satisfy repulsion by keeping a distance from each other in the form of two bond angles. The one is 120 degrees and the other one is of 90 degrees. If I say among this one and this one, it is of 90 degree, and if I say about this planar one, that is the trigonal planar one form, so it will be 120 degrees, right? Now the shape or the geometry which it can have, that is trigonal bipyramidal geometry. Phosphorus belongs to the nitrogen family. It also has five electrons in its outermost shell. All of the five are utilized in the structure, that is PCl5. Okay, now come to the next. Now here it is given ammonia molecule. Ammonia have the formula NH3. The configuration of nitrogen is as it is the central atom. It is 1s2, 2s2, 2p3. It has 3 unpaired electrons with it, and one of the lone pair is also present in the outermost shell. So it will form 3 bond pairs, or it will share 3 bond pairs with that of hydrogen atom, and one of the lone pair will hold the apex of this nitrogen. So there are present two types of the repulsions. One, that is bond pair to bond pair repulsion. The other one is the bond pair lone pair repulsion, right? The influence of lone pair to bond pair repulsion is more as compared to that of a bond pair to bond pair repulsion. This lone pair will occupy more space and it will be nearer to the nitrogen atom, just making the hydrogen bonds, or you say the bonding pairs, to come closer, reducing the angle from the regular tetrahedral geometry. It will turns to 107.5, and the geometry, it will no more be a tetrahedral geometry, but the parent geometry will change into the trigonal pyramidal geometry due to the presence of a lone pair in it. Lone pair influence the geometry, but it is not the part of the geometry, right? Geometry is mentioned by the bond pairs only, right? So that the geometry is here, that is trigonal pyramidal geometry. It holds with an angle of 107.5, which is less than that of the regular tetrahedral angle, that is 109.5. Okay, now come to the next one. One to more, that it is the type that is called AB3E. You can see 4 pair of electrons are here, but there are present the 3 bond pairs, while one lone pair is also present, represented by E, as I told you earlier. Now here we have the central atom with the 4 electron pairs once again. The example is of water. Now water the central atom is oxygen. Oxygen with 8 atomic number. It is having the geometry, that is 1s2, 2s2, 2p4. In this 4, you can see S2 is completely filled and one of the p orbital is also completely filled. So it has 2 unpaired electrons and 2 lone pairs in it, as this configuration is telling. Okay, so this central atom will get bonded with 2 of the hydrogen, with 2 of the unpaired electrons, making 2 bond pairs. Still it has 2 lone pairs which will occupy the separate place on the hydrogen atoms in the empty orbitals, right? So the shape according to the 4 pair of electrons surrounding the central atom, it should be tetrahedral, but only 2 of them are the bond pairs which will determine the shape, while the others, that lone pairs, they will influence this shape, right? So there can be the 3 types of repulsions which is found in it, that is lone pair to lone pair, and lone pair to bond pair, and bond pair to bond pair repulsion. Here the tetrahedral geometry changes to a V-shaped or a bent geometry or an angular geometry. This is due to the presence of 2 lone pairs in it, which will occupy the space nearer to the central atom oxygen, as they are attracted by oxygen only, right? So that they will occupy more space as compared to the bond pairs. The angle becomes reduced in this tetrahedral geometry once more. It becomes 104.5. Now these molecules are not discussed earlier, but they are coming under the same headings. Carbon dioxide comes under the heading of AB2 type, although it has multiple bonds in it. Similarly, methanol, or it is called formaldehyde, it is having geometry of AB3 type, while this SO2, it holds geometry. It is the member of AB3, but as there is doesn't a lone pair, So it holds A, B, 2, E type of the structure, right? Now here it is. Carbon dioxide. This point was left in the previous one lecture, that multiple bonds, when they are directed towards the same atom, they are taken or considered as one bond due to the direction, right? So in carbon dioxide, although carbon is sharing 4 of the electrons with the 2 oxygen atoms, but due to direction, we will consider them as the single bonds. So the geometry which is present, that is the linear geometry, and the angle will be of 180. 2 bond pairs are thought to be present around it, and none of the lone pairs present in it. Similarly, in methanol or formaldehyde, it is showing you the arrangement of AB3 type, in which central atom is C, which is linked with 2 of hydrogen and doubly bonded with 1 of the oxygen. As I told you earlier, double bond or the triple bond will be considered as a single bond when it is in between the 2 similar atoms. So due to direction, they are taken as one bond. So that's why the geometry will be trigonal planar, as there are 3 bond pairs at the maximum repulsion. All these are the bonding pairs, none of the lone pairs present in it. So it will hold the 3 electron pairs surrounding it, and no any lone pair will be present. Similarly, the same structure is given by SO3, that also comes under the same heading. SO3 holds this type of structure. Sulfur with 6 electrons in its outermost shell makes 2 bonds with each of the 3 hydrogen atoms. So as they are directed towards that of the same oxygen with the double bond, so all are considered as one bond. So we can say it is also a trigonal planar molecule with 3 bond pairs in it, and all these are the bond pairs, none of the lone pairs present, right? And the angle will be of 120 degrees. One of the case, when in this SO2, if there is present a lone pair, now show it like this, that replace this pair of oxygen from it, replace this oxygen from it, and it will carry a lone pair on it. It is the type, the main type is 83, but as it holds a lone pair with it, so it is AB2E type, where AB bonding pair and E is the lone pair present in it, right? So the shape will be a bend shape, as in trigonal planar geometry is the parent geometry, but as there is present a lone pair and this repulsion causes the bond pairs to come closer, as I told you earlier. 2 types of repulsions are there, as there are present 2 types of the bond pairs and lone pair as well. So you have to say there are present 2 bond pairs and 1 lone pair with this sulfur dioxide, right? This is all about that of the. Now students, after this VESPER theory, the second theory is called valence bond theory, VBT, which treats the orbitals under the wave mechanical treatment. Now here the concept is based upon the wave mechanical treatment of molecules. 2 scientists, Hitler and London, they found the bond energy and bond length of hydrogen based upon the wave mechanical treatment of orbitals, and it is termed as the valence bond theory. It was further modified by the 2 scientists, that is Pauling and Slater. As I told you, that this concept of valence bond theory is based upon the wave mechanical treatment. Under this theory, the atoms, when they undergo bonding, their half-filled or partially filled orbitals, they overlap with the other orbitals of the other atoms, and they form the new one bonds. These bonds, the determination of shapes depends upon them. So it is termed as valence bond theory, right? Now it involves only the valence electrons that is the electrons which are present in the outermost orbit of the atom. They will undergo bonding to give the new one bond formations, right? Now here the postulates of VBT are given. For this purpose, just consider the two atoms. Suppose we want to make the molecule of hydrogen. You know very well what is the configuration of hydrogen. Each hydrogen atom is having configuration 1s1, right? First orbit, that is having s orbital in it, and this s orbital is half filled. You also are familiar with the shape of the s orbital, right? It is spherical. I will say one spherical orbital of this one hydrogen is having one electron in it. It is considered as the partially filled orbital. Similarly, here we have the second atom of hydrogen. Again, it has s orbital in it, which is half filled or partially filled. Here it also carry an unpaired electron in it. Both of these orbitals, they are s orbitals. They have spherical shape and they have one electron in each. Now come to the first postulate. Only half-filled orbitals take part in bond formation. Means these two orbitals of hydrogen which are half-filled, they will overlap to produce a bond between the two hydrogen atoms, right? Now, number of bonds formed by an atom is equal to its number of unpaired electrons. You can see in this example of hydrogen, each hydrogen carry just one electron in its s orbital. So only one overlap is possible, means only one bond can be formed between the two hydrogen atoms. The third one is a molecular orbital is formed by the linear combination or linear overlap of the atomic orbitals. These two orbitals, they belongs to separate orbitals that are these two orbitals, they belongs to separate hydrogen atoms, right? When they will overlap to form a bond, here these are the nuclei of these two atomic orbitals. They will overlap in such a way so that their nuclei are lying on the same axis. This is called a linear overlap, right? They will be arranged linearly to each other with respect to each other. Now, the next one is the pairing of electrons results in bond energy. Now, remember it. When the two atomic orbitals were separate for each hydrogen, they have high potential energy, high energy. They want to become stabilized by making a bond of H2 molecule. So what will happen? They will come to such a distance to each other that the attractive force between the two orbitals become maximum and the repulsive force become minimum, right? In doing so, they will decrease their potentials. They will come to such a compromising distance when attractive force is maximum. When they are coming to that of the low energy state from the higher energy, it means they will lose the amount of energy, right? Which will comes out as the bond energy. Okay, now the next one is the electron pair is localized between two nuclei, means it is the fixed that the bond pair is present between the two nuclei at this central axis. This central axis is holding the electronic cloud. So this is called a localized region, means one knows that here the electron density is present. Now the next one is the overlap is a measure of the bond strength. Yes, greater is the overlap, means the regions they are overlapping, that is maximum, means greater is the amount of energy released, as the bond length will be short in this case. And if less is the overlap, then there will be minimum amount of energy given out, as the bond length will be large, right? Now, the next one is the line joining the nuclei of the two bonded atoms is termed as bond axis. Yes, it is given as I told you earlier. This central axis at which the linear joining of the two atomic orbitals took place to give a molecular orbital. This is termed as bond axis. Right? Now the overlapping orbitals are required to have same symmetry. You can see both of them, they are the spherical ones. Right? They having the same shapes. Okay. Now the next one is with respect to that of the bond axis. It accounts for the ionic character of a covalent bond and the hybridization of atomic orbital. Here the example given to you is of a heteroatomic molecule, that two hydrogen of the same type, right? They are going to overlap to give the molecule of hydrogen. Now there is no difference of any sort of electronegativity, ionization potential, energy, or whatever, the size or anything between the two hydrogen atoms. So there will be no any ionic character. It's a pure one covalent bond. Dipole moment of this one is zero. No ionic character is there. Ionic character appears when two dissimilar atoms they join. For example, if I say one of the hydrogen and the other is the Cl, which will use its p orbital for the bonding. It's the overlap of H with the Cl. Now you can see two atoms are different, fluorine with high electronegativity and hydrogen with the less electronegativity. Here we will say the domination is of fluorine due to electronegative character. So the bond pair will be more towards fluorine rather than towards hydrogen. So this one will give rise ionic character to this covalent bond. Although the bond between them is covalent, but there will be present polarity within the molecule or the separation of charge due to the electronegativity difference between the two bonded atoms. Right? This will also be considered when we are dealing with the VBT. The second term used is hybridization of atomic orbitals. This a central atom undergoes before bonding with that of the other atoms. Right? This is the mixing of orbitals. You will do it in detail in the same lecture, that is VBT. Under this VBT, we will do that hybridization as well. So for the time, I'm just going to leave it here. Now here some of the drawbacks of VBT are also mentioned. It has some limitations. It is not going to explain the coordination, covalent bond formation in the molecules. Coordinate covalent bond is formed between the two species. Among them, first one is a pair, one is a group of atoms. It's or you can say it is a covalent compound which will get bonded to that of an electron deficient species, right? For example, the formation of ammonium ion from NH3 uh, and H plus overlap. Now, the bond between nitrogen and hydrogen will be based upon the lone pair present on this nitrogen. When the whole pair is given by one species, it is termed as the coordinate covalent bond. So, it is not going to explain it as it deals with the partial field orbitals, right? So, how will we explain the formation of NH4 plus ion? Now, the second one is it cannot explain the formation of odd electron molecules or ions, for example, carbon monoxide formation, right? Or the NO2 formation, NO2 formation, and it is not going to explain the paramagnetic behavior of oxygen molecule. Paramagnetic behavior comes out as I told you earlier. Do you remember? It is under the influence of magnetic field. When it gets attracted in the magnetic field, we say it is the paramagnetic behavior which is shown by the oxygen molecule as it still have unpaired electrons in it. How is it possible? Under the VBT. So VBT is not going to explain the paramagnetic behavior of oxygen molecule. These are some of the drawbacks of VBT. Now next there comes two types of bonds they are considered in case of the VBT. Every time you have to talk about the sigma bonds or the pi bonds. Now how these bonds are formed, this is given here now. The sigma bond are formed by the linear overlap of the two orbitals on the bond axis, right? Now here the maximum charge density or electron density is lying on the central axis. Here you can see in this case two half-filled orbitals, they overlap on the same axis, their nuclei are lined, their overlap is maximum, and after overlap the maximum electron density is lying on the central axis. This is called a sigma bond formation, right? For example, when consider these two orbitals as the orbitals of hydrogen. When hydrogen orbitals, as I told you earlier, they have the configuration 1s1. When the two orbitals, they will join by the 1s overlap, each is holding one electron in the orbital, so they will form a sigma bond as their linear overlap takes place on the joining axis. They are placed there in such a way that their nuclei are present on the central axis and the electronic cloud is localized here. It is also present on the central axis, right? So this is termed as a sigma bond formation, right? Similar bond formation can occur here in nitrogen or in HF, but the orbitals will be different. Here it is S to S overlap. Whatever the orbital it belongs, every time S to S overlap will give you a sigma bond, right? Similarly, if the one of the s orbital and the other p orbital, they are going to overlap linearly in this way, they will also hold a sigma bond. This is s and p overlap, right? As it occurs in case of hydrogen fluoride. And if I say I have to make N2, then there will be two nitrogen atoms with their p orbitals lying on the central axis like this. So this is P to P overlap. So we can say three overlaps will give you the sigma bonds. This can be S to S orbital overlap. This can be S to P orbital overlap, and this can be P to P, which is lying on the central axis. That will give rise the sigma bond. Remember, among p orbitals, as there are three p orbitals designated as px, py, and pz, only one of them will go for the sigma bond formation, the other two will go for the pi bond formation. Now the next one is, these are the pi bonds. You can see here the shape of p orbitals, that is the dumbbell shape. They are lying above and below the central axis. Their loops are arranged so when they overlap, the central region or the line of joining remains empty. No electronic cloud lies here, but the region appears by the overlap of these two, and these two lobes will give rise to the electronic cloud present above and below the plane, right? So this is termed as a sideways overlap or a lateral overlap. They are lying perpendicular to the central axis, right? So this joining will give rise the pi bond formation, right? Where the electronic cloud is lying above and below the central plane. Remember, among p orbitals, after the formation of one sigma bond by p orbitals, the remaining two will undergo for the pi bond formation. Now students, difference of the orbitals will be discussed in the next lecture. Okay.